All right. Hi, everyone, for our final but certainly not least award for this meeting. Before I do the introduction, I just want to give a plug or suggestion. If you have someone in mind that would be a good fit for one of these ASLO awards, please nominate early and often. The nomination portal is open. It closes in October. But if you have any questions about the nomination process, please don't hesitate to reach out. We're really trying to increase the number of awards or nominees that we get and the diversity of nominees that we get. So please don't hesitate. But I do want to now turn to our final award. I want to thank the nominators and the subcommittee for all their effort on this award. The G. Evelyn Hutchinson Award is awarded to a researcher who has made significant contributions to knowledge in limnology or oceanography, and in particular whose future work promises a continuation of scientific excellence. This year's awardee has distinguished himself as a pioneer in the field of marine science, conducting groundbreaking research on a large range of topics, including Antarctic biology, ecosystem-based management, kelp forest ecology, and an impressively large body of work on marine heat waves. As a leader in marine heatwave research, he has been instrumental in unifying an empirical definition of these extreme events, which has been adopted by the research community and policymakers. He currently leads a vibrant and inclusive research group, and his colleagues write, quote, "His work has provided options for those seeking to manage coastal ecosystems faced with unprecedented environmental change." Please join me in congratulating Dr. Dan Smale as the 2025 Hutchinson Award winner. Yes, we could clap. Unfortunately, Dr. Smale couldn't join us today, but he has sent in his remarks, so enjoy. Thank you.
Good afternoon, everyone. First of all, please accept my apologies for not being able to receive this award in person. I really wanted to attend the meeting in Charlotte to meet some of you and learn about some of the incredible science happening across the ASLO community. But unfortunately, for a number of reasons, it was not possible to travel. Second, I want to express my sincerest gratitude for this prize. It really is an unexpected honour, and I'm genuinely shocked and thrilled. So thanks to the awards committee who accepted the nomination. And to be in the company of some of the truly great aquatic scientists that have won this award in the past is both gratifying and somewhat mind-blowing. So thanks again. I'm just going to share a few slides. So as we all know, marine science is not a solo sport, but very much a team endeavour. The research I'm being recognised for today would simply not be possible without all the amazing collaborators I've been lucky enough to work with over the past 20 years or so. Our work on marine heat waves in particular has been impactful, and I'd like to accept this award on behalf of the International Working Group on Marine Heat Waves, which we started back in 2014 in Perth in Western Australia. Working with this dynamic group has been one of the highlights of my career to date, and I've learned so much from these inspirational scientists and people. In particular, I'd like to thank Thomas Wernberg, Eric Oliver, Neil Holbrook, Alistair Hobday, Alex Sengupta, Pippa Moore, Mads Thompson, Mike Burrows, Karen Philby-Dexter and Katie Smith for their key roles in this research area and for being not only great collaborators and amazing scientists, but also great friends. And I should mention Katie Smith again, as she was the one who nominated me for this fantastic award in the first place. I'd also like to acknowledge past and present members of the Beach Group that I lead here at the Marine Biological Association in Plymouth. I've had the privilege of working with many talented postgraduate students and early career researchers over the past decade or so. And despite various challenges and obstacles along the way, we've managed to stay positive and productive and had some great times along the way. So thanks to all these incredible early career scientists. And just finally on the thank yous, I just wanted to mention all the participants of the various Team Kelp UK field trips over the years, which have been extremely fun and enlightening and allowed us to learn a bit more about these incredibly important kelp forest habitats. In particular, I'd like to mention Nathan King and Pippa Moore, who endured many, many weeks in the field with me and have contributed to all the research outputs from the project. Okay, I'm just going to very briefly present some science slides focusing on the science of marine heat waves and where we are in the field. So I'm sure everybody in the room knows that the heat content and temperature of the upper layers of the global ocean is now at a record high. This plot on the left just shows globally averaged sea surface temperatures over 150 years or so, and there's a very evident steady but significant increase in global average sea temperatures. And when we look at individual years represented by these squiggly lines, each line is a year within the satellite temperature record. And recent years, 2024 shown in orange, 2025 in red, and also the grey line behind me in 2023, have been exceptionally hot compared to the long-term average. And this has led to widespread, very high sea surface temperature anomalies distributed around the global ocean. And the underlying cause of this is, of course, anthropogenic global warming, as the upper layers of the global ocean have absorbed around 90% of the excess heat trapped in the atmosphere. But as well as this gradual increase in average temperatures, we've also seen an increase in the occurrence of discrete extreme warming events or marine heat waves. But actually, until we published this paper back in 2016, there wasn't kind of a widespread, widely accepted and used definition of what a marine heat wave actually was. So we, as part of this first workshop, locked ourselves in a dark room with some atmospheric climatologists and came up with this quantitative definition, which has now been widely adopted by the marine science community. So a marine heat wave is a period of 5 or more days where water temperatures are warmer than the 90th percentile based on a long-term 30-year, for example, climatology for that time and place. We then followed that up with a subsequent paper that categorized marine heat wave based on their severity. And once you have this quantitative definition, you can then track marine heat waves across space and time. So this example is from Southwest Australia in 2011, which I'll come back to, and that shows the maximum aerial extent of the event. And this is a time series which shows temperatures increasing to the peak of the marine heat wave and then decaying for some weeks afterwards. And once you have a quantitative definition, you can then compare marine heat waves across different events and different regions. So things like the maximum or the cumulative intensity, the duration or the timing and the rate of onset can be compared across different events. And using this definition, we then examined trends in marine heat wave activity over long time periods and showed that over almost a century, globally average marine heat wave frequency increased by 34% and duration increased by 17%. So these events were not only becoming more frequent, but when they did occur, they were becoming longer. And this led to a 54% increase in annual marine heat wave days globally. And we've done a recent analysis of recent years using the same approach, showed that this trend has actually accelerated in recent years. And in a paper we published in Nature Climate Change just last week, we showed that summertime marine heat waves in the summers of 2023 and 24 were unprecedented. So we're really seeing a stepwise increase in marine heat wave activity around the world. And these marine heat waves had a wide range of impacts in both in all biological, physical and societal spaces. So I'm a biologist or ecologist, so why are marine heat waves important? Well, temperature influences all biological processes, and that's because species have evolved to occupy a thermal niche or tolerance window, and when temperature thresholds are exceeded, ecophysiological performance can decline very rapidly. So every organism on Earth lives within this temperature window, this thermal performance curve, and can operate at a minimum temperature. And as temperatures increase, performance actually increases up to an optimum temperature or T-hot. But if temperatures continue to increase, then ecological performance and fitness can decline very rapidly up to a maximum temperature after which an organism can no longer function. So if temperatures experienced during a marine heat wave are stressful, performance will decline. Initially, this may look like reduced growth or reproduction or commencement of protective mechanisms, but eventually that organism must acclimatize or move or die. However, if temperatures experienced during a marine heat wave are not stressful, and this depends on the timing and also an organism's location within its wider species distribution, then increased temperatures may actually increase ecological performance. So that's the theory, but what do we see in the field? Well, perhaps one of the most well-studied examples is from a marine heat wave that happened in 2011 off the west coast of Australia. And this marine heat wave was extreme in every way. So sea temperatures were the highest on record, and they were around 4 or 5 degrees the long-term average for summer, 4 or 5 degrees above the long-term average for summer. It affected over 2,000 kilometers of coastline and lasted for over 10 weeks. So this was an extreme event. And I was working with Thomas Wernberg at the time, who had a really nice baseline data set on kelp forest structure and distribution along this coast, which we're able to use to then resurvey to look at the impacts of this marine heatwave. And we showed that in the years following the marine heatwave, the dominant kelp, Plenary radiata, was eradicated from 100 kilometers of coastline, and that represented a range contraction of its global distribution. And around 43% of forests were lost or severely decimated, which is an area of almost 1,000 square kilometers. And in almost all cases, these structurally diverse and biodiverse habitats were replaced by simple unstructured algal turfs. So this is just an example of one of the survey sites. Before the heatwave, you had a high coverage of the Kelpoclonia radiata. After the heatwave, in its place was a sort of high sediment, low structure habitat dominated by different turf-forming algae. We didn't just survey the kelps themselves, we looked at other habitat-forming seaweeds and other components of the ecosystem and showed significant declines in habitat-forming seaweeds and their associated herbivores, and also high rates of coral bleaching and, at least initially, some coral mortality. Conversely, in that system, we saw increased abundance of turf-forming weeds and some warm water fish species, and at least initially, some increased coral recruitment into the areas that were dominated by kelp forests. So this is an example of how an extreme event can alter the structure of an entire temperate ecosystem and cause a rapid phase shift towards a more tropicalized state. After this work, we wanted to see whether the responses we saw in Western Australia were kind of more general to other marine heat waves or whether they were specific to that particular region. So to do this, we conducted a meta-analysis of ecological responses to 8 different marine heatwave events. These were the ones that we can find enough information in the literature, and we're able to gain over 1,000 observations from about over 100 papers. And these events included the West Australian event, marine heatwave, but also 3 marine heatwaves in the Mediterranean and a number of different marine heatwaves associated with different El Nino events. And each heatwave had different kind of duration and intensity and properties. But all of the marine heatwaves had negative ecological impacts, but the magnitude of impact varied a lot between taxonomic groups and between types of biological responses. So certain groups shown here by the corals, other sessile invertebrates and seabirds were particularly hard hit by these heatwave events. We also looked at the ecological performance of different habitat-forming species because we know that these have elevated influence in coastal ecosystems. And we showed that the annual marine heatwave activity was negatively correlated with ecological performance of key habitat formers. So in the Caribbean, more heatwaves was linked with more coral bleaching. In Australia, more heat waves was linked to lower seagrass density, and in California, more heat wave days was linked to lower kelp biomass. We then wanted to move from just looking at communities and habitat-forming species to ecosystem services that had socioeconomic implications. And in this paper, led by Katie Smith, published a few years ago in Science, we were able to identify 34 different marine heatwave events that had some sort of socioeconomic impact since 1995. And we used this classification of ecosystem services and just showed that every marine heatwave impacted upon at least 2, but often many different ecosystem services provided by that system. Just to pull out a few different examples, in 2010, a marine heatwave caused bleaching and mass mortalities of coral in Southeast Asia, which led to losses of economic income from tourism of somewhere between $49 and $74 million. Similarly, in 2015, the closure of a recreational clam fishery led to the loss of around $40 million in tourist spending. And also, in 2016 to 17, mass mortality of farmed salmon in Chile led to around an $8 million loss of export revenue. So these things have ecological and societal impacts. There will, of course, like any disturbance, be ecological winners and losers, and that presents both opportunities and challenges. So we've shown that some fisheries and aquaculture species will do better than others, and warm adapted species in particular may profit and extend their geographical distributions or increase population size during or after marine heat waves, either temporarily or as part of longer-term range shifts. And that creates opportunities for recreation and tourism industries, amongst others. But what is clear is that marine heat waves are forceful agents of disturbance, and they are now longer and more frequent and will continue to intensify under anthropogenic warming, and that they can impact a wide range of species, habitats, functions, and ecosystem services. So I'd say where the field is now is that there's a need to better understand the variability in responses to marine heat waves, to develop more useful predictions of their impacts. And these predictions are needed to inform management and adaptation approaches. And we need both observational science from real systems and also manipulative experiments to achieve this. And really the holy grail is to improve forecasts and projections of the physical properties, the timings and the intensities of these marine heat waves, combined with an understanding of the region and the biogeography of different species and their thermal performance and thermal tolerance, and combining these biological and physical factors come up with some measure of risk that can be then used to inform management as these things happen. And that's a very sort of short whistle-stop tour of where we are with marine heatwave science. I'll finish just by thanking you again for this amazing award. If there's anything you want to discuss about heat waves or kelp forest ecology in particular, feel free to drop us an email and I'll get back to you. Thanks again, and I hope you enjoy the rest of the meeting.